Hi everyone, and thank you all for tuning in to this Macalloy webinar. Today's subject is fatigue in tension rods in civil engineering. Just to introduce myself, my name is Harry Smith and I'm a design engineer here at Macalloy. I've been at Macalloy for over 6 years now, and generally I spend my days giving technical input on any uses of our product, designing bespoke solutions for any non-standard applications, as well as developing new and existing products. And actually this is the second webinar that I've done on fatigue. If you're interested in watching the first, then please by all means head over to the Macalloy website where you can find a link to the video. Now, for those of you that have seen my previous webinar on fatigue, there will be a lot of crossover, so I do apologise if you find me repeating myself. However, the principles do have a lot of carryover and are pretty similar in both applications. The agenda for the webinar today is as follows. I'll go through a quick overview of what fatigue is and why it happens, as well as some requirements related to civil engineering. I'll then touch on a few places where we see fatigue in civil engineering, just to help you visualise it better as we're talking about the technical details themselves. After that, I'll get more specific to the product and go through the various factors that have an impact on fatigue performance and how we typically address these. And once I've gone through those factors, I can then tie them back into the examples that I mentioned earlier, giving a more complete overview. And as always, a quick summary at the end to recap what we've talked about. First up, an overview of fatigue itself. No, I'm not talking about when you're tired because you stayed up too late the night before. Materials fatigue, instead, is a mechanism of failure that comes about because of cyclic, otherwise known as oscillating loading. EN 1993 Part 1 Part 9 defines this as the process of initiation and propagation of cracks through a structural part due to the action of fluctuating stress. Just to elaborate on that, EN 1993 is the European standard for steel structures, and Part 1 Part 9 is a section in this that covers fatigue. So as this cracking makes its way through the material, you get this kind of seashore effect, leaving behind striations on the fracture face where the crack is initiated from originally and then propagated through the failed part. This crack reduces the cross-sectional area at that point in the component until it gets to a stage where it can no longer cope with this applied load. At this point, it experiences what's known as a catastrophic failure. You can see a couple of examples of this from the images on the right-hand side. So that first image on the top is just a diagram that shows how the crack propagates through the material, leaving behind those striations, and then you get the final area where that catastrophic failure occurs. And the bottom image is an example of when it actually happened. So in that image, you can see that the crack actually started right at the top of the image, and it grew through the cross-section of the bar until the remaining material could no longer cope with its applied load. Then it completely snapped, and that final fracture is that sort of bottom darker section that you can see there. Now, all of this may sound very dramatic, and more often than not, people tend to think dramatic events as quite rare. However, fatigue is actually one of the most common methods of failure in all mechanical structures. Now we know what fatigue is, let's talk a little bit more about why it actually happens. If you take the description of fatigue literally, it's actually extremely common, and by taking it literally, I mean a load that oscillates in its intensity rather than being completely static. Now, a lot of structures do actually experience a small amount of fatigue as a result of loading such as wind, for example. However, if the load itself, or the change in loads, is relatively small, the loading conditions can be considered what's known as quasi-static. Now, quasi-static basically means that from a design perspective, you can consider it to be essentially static. Fatigue loading becomes more demanding on the structure as the stress range, the peak load, and the frequency at which it changes its load increases. Now, we'll talk a little bit more about where you can typically find that a little later on in the presentation. Now, unlike the last webinar, when I say tension rod, I'm not referring to architecturally exposed structural steel in this presentation. I'm using it just as a general term, meaning steel bars that are used in tension. Requirements for a specific product, such as a post-tensioning bar or marine tie bar, are often outlined in the related standards. So for the post-tensioning bar, that would be the European assessment document related to it, and then for the marine tie bars, that would be EN 1993 Part 5. The requirements for a post-tensioning bar in fatigue are on screen now. So it needs to withstand 2 million cycles with a stress range of 80 megapascals and a peak stress of 65% of its ultimate tensile strength. The stress range is the difference in stress experienced by the material as the load increases and decreases in its fatigue cycle, and the peak stress is the maximum stress experienced within these fatigue cycles. Any PT bar designed to be in accordance with the EAD must be able to withstand a test with these parameters, as is the case with other products and their relevant standards. Other readily used products, such as 8.8 volts, have no fatigue requirements within their standards. Now, while it's entirely feasible that they could pass these tests, less data exists to support this. You can compare the stress range on a material against the likely number of cycles of failure using an SN curve if the data exists for the product that you're looking at. You can see an example of this on screen now. This graph can give an approximation of how many cycles a component is likely to withstand, found on the x-axis, when subjected to a given stress range that's found on the y-axis. This data is plotted using a logarithmic scale to keep it on a straight line and easy to interpret, but don't worry, I'm not about to kick into a maths lesson. While I'm here to talk about tension rods, in ground or civil engineering, steel bars are often surrounded by much weaker material, such as concrete, grout, or soil. Often in a fatigue setting, it's this weaker material that is the limiting factor, depending on the design of the structure. It's also important to make reference to the fact that in some civil engineering applications, there is a lot of redundancy in the system, with the serviceability limit state, loading, being well within the capacity of the bars. So SLS loading, if people aren't aware, is just the loads that the bars themselves experience on a regular day-to-day basis. What this can mean for the bars is that for a similar stress range, the mean or average stress, along with the peak stress, is lower, and this reduces the fatigue demands on the system. By no means is this an exhaustive list, but these are a few examples of applications that can experience fatigue. Now this is to give you an idea of the application so you can relate to it when we're discussing more detailed points later on. Structural sections that are bolted together using steel bars such as bridge decks or maybe gantries can be subjected to oscillating loads as the structure is loaded and the sections move relative to one another. Holding down bolts are a product with widespread applications and can vary from wind turbines to flood defense anchorages and many more. Often the devices or structures that they are holding down are subject to a plethora of loading types that are repetitive and therefore cyclic. Geotechnical works, including rock bolts, soil nails, or post-tensioning bars, are often subjected to a combination of oscillating forces that are minor when only one of them is considered, but when occurring simultaneously, they can amalgamate to a demanding fatigue loading. Finally, applications in ports, such as marine tie bars that are buried under a mound of earth and shipping containers. Now, these can be subjected to fluctuating load and cannot be inspected, so appropriate fatigue allowance has to be put in place. Obviously, these are just examples, and each structure or application should be assessed based on its own conditions or requirements. Now we'll talk about what factors in tension rods affect its fatigue performance, and how these can be improved. The first of the factors we'll talk about today is the bending moment. This is an additional source of stress caused by a force trying to deflect the material that is cumulative with stress caused by the axial loading of the tension rods. Now, on occasion, it is manageable if the fatigue requirements are low or if there's a lot of redundancy in the member. However, if the fatigue loading is harsh, a bending moment amplifies this significantly. The reason behind this is, as the load oscillates, and then the stress does with it, the two stresses change independent of one another. So if the stress range because of the axial load is 50 newtons per millimeter squared, and then the stress range as a result of the bending moment is 50 newtons per millimeter squared, that localized stress range is 100 newtons per millimeter squared, and that's much more likely to lead to cracking than if the bending moment wasn't present. Typically for rods in civil engineering settings, such a bending moment is caused by the fittings at the anchorage being misaligned and that angle being taken up by the more flexible bar, or perhaps any horizontal force being imparted on the bar by settlement of earth, ground, or concrete. As the end anchorages are more often than not a nut and washer bearing against some kind of plate or wall, the best solution to accommodate this misalignment is changing flat mating surfaces out for sphericals. An example of this is shown on the upper image. The mating radii of the spherical nut and washer allow for full bearing contact to be maintained between the two without having to bend the bar to do so. They can typically handle up to 3 degrees in any direction. Now if you need to accommodate larger angles, a tapered end plate should be used. Lateral forces acting on the bar can be dealt with using what we call an articulation joint. This can be observed in the lower image. Adding in a pin joint, or typically 2 pin joints, into the main body of the bar allows for the bending force to be entirely coped with the 2 localized connections that are designed to be able to rotate. This is because the pin allows for the rod to articulate about the joint without any component having to bend or deform to do so. With the use of the aforementioned connections, the area that experienced the bending stress in a standard system no longer has that additional source of stress. This reduces peak stress and stress range, thus improving the fatigue life of the system. Just as geometry affects the fatigue performance of the anchorages, the geometry at any point in the load path can affect the rod's performance in fatigue. Any corner or change in thickness can result in the stress concentrating at one point, with the sharper the corner is, the greater the concentration. Now, while the stress evens out in areas away from the transition, the stress is compounded at that corner, forming a stress razor, otherwise known as a stress concentration area. Just as with bending moments, a concentration of stress at one point correlates to a larger stress range as that load fluctuates. Now this in turn reduces the fatigue life as stress razors are hotspots for crack initiation. The most commonly present example of this in bars and civil engineering is actually the thread form itself. Now, while it's impossible to get a perfectly sharp corner in the root of the thread, some threads, such as the standard metric thread seen in the top image, have a relatively small root radius. The smaller this root radius, the more it can act as a stress concentration area. So in order to reduce demands as much as possible, this should be the largest possible radius. An example of such a thread is the Macalloy thread form used on all of our 1030 bars, as seen in the lower image. Both of these threads have the same 60 degrees inclusive angle on the fundamental triangle, but the Macalloy thread form has a very large root radius, and as a result is a very fatigue resistant thread form. The presence of a radius will lower the fatigue demands in any component if placed appropriately. The thread form is merely an example, but this extends to couplers or turnbuckles too. Another aspect that affects fatigue regarding the thread is actually how it's created. So there are two main methods of achieving a thread form from a solid bar. The first of which is a cut thread. Now this is where you start with a bar that is the same diameter as the major diameter or peak of the thread, and you achieve the thread form by removing material with a cutting tool. Now in doing so, the tool is breaking through the grains of the steel and leaving exposed grain boundaries on the flanks of the threads. Now this is an issue in fatigue applications, as these exposed grain boundaries are areas that cracks can initiate. The second option is to roll thread the bar. Now this is where you start with a smaller bar, approximately around the effective diameter of the thread, and the bar is then introduced to three dies known as rolls, and these dies spin circumferentially around the bar, and are then forced into the material. So the rolls manipulate the steel. The material that is displaced, creating the minor diameter or the trough of the thread, is then forced upwards to create the major diameter or peak of the thread. So this is the method that we actually use at Macalloy, and as well as the weight and cost savings of using less starting material, the grain boundaries are not left exposed on the flanks of the thread as they are with the cut thread. Now you can see this from the image in the bottom right hand corner there, where these grains of the steel have been deformed and rounded as the thread has been rolled on. Now this means it's more difficult for a crack to initiate. The final factor we'll talk about in this presentation is preloading of the tension rods. Preloading is the process of actively putting tension into the bar before construction is complete and the structure is put into service. On such groundworks, more often than not, the end anchorage will comprise of a nut and washer, so the tensioning is performed with a hollow ramjack such as the one shown in the upper image. The video playing now is a good representation of what the actual post-tensioning procedure looks like, or the pre-tension as I mentioned in the slide there. So we're panning around now to the live end or the jacking end where the actual tensioning is going to be performed, and then the equipment's going to fly in one by one and show you the procedure. So first of all, you've got the ring spanner, which allows you to rotate the nut. Then you've got the bridge coming in, which actually gives access to the ring spanner, the jack that provides the force, and the puller that connects it all together. That puller is then pushed outwards by the jack, and then the nut is rotated via the ring spanner to lock that load off. Now I apologise if I spoke a little bit fast there, but I was just trying to keep up with the video. So generally the procedure of what happened is the fact that the load is imparted onto the bar, causing it to stretch. Then that nut is butted up against the actual concrete structure itself or the end plate that it's bearing against. Then once that load has been released by the jack, the bar tries to go back to its original length, however the nut prevents that happening, causing a compressive force to be applied on the structure itself by the bar. This is typically done in order to minimize or mitigate any amount the bar will stretch during the life of the structure when subjected to load, as this elongation has already been taken out by the preloading process. It also has a significant impact on the fatigue performance of the member. So in table 8.1 in EN 1993 part 1 part 9, there it is stated that for preloaded bolts the reduction of stress range may be taken into account. Preloaded bars are already under stress, as this stress will not change until the force in the member has been overcome or a secondary source of load such as a bending moment is applied. Because of this, the actual stress range while in service can be minimised through preloading, which significantly reduces the fatigue demand on the system. As well as reducing the stress range in the bar, preloading can actually minimise or even prevent fatigue loadings themselves from occurring. This is due to the effect that the induced load has on the surrounding system. One such example can be seen in the diagram on screen now. The left-hand image shows a bolt that has not been preloaded. The two plates move when they experience force, and this in turn imparts a shear load on the bolt. If oscillating, this shear load can translate into a fatigue load and over time result in failure of the bolt. The right-hand image shows a bolt that has had a preload induced into it, which in turn is clamping the two plates together. Now when the plates experience the same force as mentioned before, the friction generated by the preload prevents any movement. This keeps the bolt central and it negates any shear loading. No load imparted means that no fatigue load can be experienced, and this is true with other loading sources such as bending. This indicates that a well-designed and well-placed preloaded bar or bolts can have benefits on the structure that go beyond its own performance. I mentioned earlier in the presentation that there are product requirements for fatigue outlined in their relevant international standards. Over and above these, there are a number of regional standards for products that have more demanding fatigue requirements for the system to pass. ASQPE is the French post-tensioning standard, and this has a much higher stress range of 180 megapascals and a peak stress of 70% of its ultimate tensile strength. And BMVI is the German Infrastructural Authority, and this has similar requirements, though you can see from the table on screen that it breaks down its systems into two classes depending on the stress range that they can withstand in a test, with class 1 being the harder to pass. Both of these criteria are much harder to pass than the standard requirements outlined in the EAD. These tests are in accordance with the relevant country's design codes and need to be passed in order to be used in all appropriate structures. While efforts should be made to minimise or mitigate fatigue stresses, it's not always possible. Thus, it's necessary to have a product with good, proven fatigue resistance. And I'm very proud to say that the Macalloy 1030 bar is one such product. It's passed all the ISQPE fatigue requirements and has achieved Class 1 accreditation in the BMVI testing standards. Now we've talked over the various factors, I'll talk a little bit more in detail about the various examples that I touched on earlier. The first application is bolting together structural sections, and the best example I can think of is connecting two decks along the span of a bridge. As the traffic on a bridge passes over it on a day-to-day basis, the weight of those vehicles imparts a force that wants to move each bridge section relative to its neighbours. The high volumes of traffic quickly racks up the number of cycles, and the stress range can be high due to the vehicles such as cars, trucks, or even trains being very heavy. The forces would be a combination of shear, bending, and via prying some axial force if left alone, giving the potential for some huge stress ranges. I mentioned earlier about how pre-tensioning the bar can reduce the fatigue demands on the system, and this is much more practical than having to upsize the steelwork in order to cope with this fatigue loading. This is exactly one of those situations. The clamping force between each section minimises the movement and by extension reduces the fatigue demands on this component's experience in these loads. This was utilised on the third Bosphorus Bridge, where a number of preloaded Macalloy 1030 bars were used to connect the various bridge sections together. One that's very similar to the last example in terms of loading, but still an application very much worth mentioning, are holding down bolts. So the example that you can see on screen and that I'll talk about is wind turbines, but the possible uses for holding down bolts are far more widespread. The wind turbines are held to their foundations by a ring of bolts. You can see this in the right-hand image. As the wind buffets these turbines and those blades swing around, the turbine itself wants to rock. Now these forces are taken out on these bolts, and like bridge sections are a combination of shear, bending, and via prying some axial force, giving the potential for that massive stress range. As with the last example, preloading the bolts in the foundation actively clamps it down, both minimizing movement and reducing any likelihood that the stress in the bars will significantly change. While beneficial, even preloading cannot completely mitigate fatigue demands, so a tested, fatigue-resistant product is necessary for complete assurance of performance. Post-tensioning bars or other high-strength studding such as our S650 bars are used in a complete smorgasbord of geotechnical applications. These include rock anchors for holding back sections of cliff or rock face, soil nails in order to stabilize ground conditions on slip plains or other loose earth, reinforcing sections of ground or concrete in areas such as tunnels, and also to assist in seismic damping to act as the main load resisting element. Various phenomena such as vibrations or thermal changes can subtly alter the loads these bars experience. Independently, each of them wouldn't give the system too much trouble, however they seldom work alone. The combination of more than one of these conditions can accumulate cycles quickly, and if working simultaneously, they can result in larger stress ranges. Both of these worsen fatigue demands, so having a bar that resists fatigue in such a manner is very important to reduce the risk of failures and negate the need to replace any bars before their intended service life has elapsed. Finally, marine tie bar works are a growing industry, as more and more goods being sea freighted has resulted in more and more port space being needed. A common feature in the construction of such ports is a retaining wall that holds back the earth and concrete supported by tie bars. You can see a good example of this on the bottom image. This is such a port before it has been backfilled with soil and then topped with concrete or asphalt. The wall at the top of this image holds all this material in place, with the rods anchoring it back. As this weight acting down on the port is proportional to the force trying to push the retaining wall out to sea, This is proportional to the load imparted on the tie bars. So as this load fluctuates as cranes move and operate and containers are loaded on and off ships, the load in the tie bars changes. As you can imagine, the frequency of this will be lower than in previous examples, but as there is no way to inspect these bars once they've been installed, ensuring fatigue demands are minimised is best practice for a sound structure. In marine tie bar applications, there is not often significant preload, so ensuring the absence of bending moments is priority. The use of articulation joints in the body of the bar and spherical nuts and washers at the ends gives the bars the greatest capacity and minimises fatigue demands. So, to summarise, stress range, maximum or peak load, and frequency are key values when assessing the fatigue performance of a tension rod. The geometry of components on the load path affects the fatigue performance as well as the properties of the material itself. Stresses in the material coming from loading other than axial tension tend to significantly increase the localized stress ranges. And high, localized stress almost always results in a high stress range, which is detrimental to fatigue life. Preloading bars can often reduce fatigue demands on a system. Systems tested to prove their fatigue resistance in accordance with standards give confidence in performance. And finally, designing to deal with fatigue demands in conjunction with selecting a proven product puts you in the best position to prevent fatigue failures. That's the end of the presentation. Thank you so much for logging in and taking the time to listen. I hope you found it useful, interesting, or even both. On the screen now, you can see my contact details, as well as the general technical inbox that all of my colleagues in the engineering department have access to. Please feel free to get in touch. We would love to hear from you.